Hello. Yesterday we have discussed about the one of the route that is used to produce the dipropylene glycol. Today we will discuss more on the route number two, that is hydrolysis of propylene oxide over a solid base catalyst. In this method, what we have done, the PG and DPG produced through hydrolysis of propylene oxide over a solid base catalyst. So reaction standpoint, the chemistry or the reaction will be same as the earlier method, but here we are gonna use a catalyst, solid base catalyst. So here there is a one table that describes the conversion of PO on different catalyst. So if you are use ZiO2, the conversion of PO will be 5.1 and selectivity for PG is 100%. There will be no DPG. If you use tantalum oxide, the conversion of propylene oxide will be 10.2%, while the selectivity of PG still remain 100%. There is no DPG. So these above two catalysts can be utilized to produce the PG through propylene glycol through propylene oxide. But as we use HZSM5, the PO conversion increases to 23.2%. We get 94.8 propylene glycol and 5.2% selectivity of dipropylene glycol, and TPG still remains zero. As we use SO3 type resins, the propylene oxide conversion goes to 99.9%. Selectivity of PG become 46.2%. Selectivity of DPG become 41.3%, and that of TPG become 12.5. So here you can realize the last two options may be utilized to produce the dipropylene glycol through propylene oxide. Now, as we discuss the route 2, now we will move on to the route 3, that is liquid phase dehydration of propylene glycol. So here we use the solid acid catalyst to dehydrate propylene glycol. PG under the influence of Amberlist 36 dry and MFI framework geolite catalyst produce acetone, propanoldehyde and DPG. So here the reaction is given. So here you can see, here we have propylene glycol. It is converted to dipropylene glycol and water, or it can produce propanaldehyde plus water, and then it further converted to ethyl methyl dioxylane EMD. Similarly, it can produce acetone plus water, and then it again converted to trimethyl dioxylane TMD, because here we are doing dehydration. So at every stage you see there is a water molecule that is removed. At every stage of reaction there is a water molecule that is removed. That's why the dehydration of acetone and propanaldehyde is possible to further in EMD and TMD respectively. So in this reaction, what you can see in this route, there is a high possibility that there must production of propanaldehyde, acetone along with the dipropylene glycol DPG, because this is a dehydration reaction and we might not have a control over this. Now we will discuss about the route 4, that is synthesis from propene. So in this route, we will study a method which involves a phase transfer catalyst. So what is a phase transfer catalyst do? It transfers the reactant, and when reactant and product are in different states, gaseous, liquid or solid, then we use these catalysts to phase transfer the product into the in a different phase other than the reactant. So in this, there is a heteropolytungsten used to convert propene in presence of hydrogen peroxide to form 1,2-dipropiondiol DPG and TPG. So here the reaction is given. You can see it's converted to DPG, propanediol and water. So this reaction involves two steps. Step 1 of reacting propene with hydrogen peroxide in presence of catalyst, phase transfer catalyst and polytungsten to form the desired product. This is an organic phase liquid state reaction. Step B, separating the reaction mixture into aqueous phase comprising of 1,2-propanediol, DPG, TPG and an organic phase. So In the route 4, we will have a phase transfer in which we will have aqueous phase and organic phase. So aqueous phase will consist of propanediol, DPZ and TPZ, and organic phase will have the other products. In the route 5, synthesis using propylene by propylene oxide route. So here what happens? Propylene react with NaOH, Cl2 to produce propylene oxide, and that propylene oxide when hydrated produce DPZ. When the propylene oxide react with DPZ, it produces TPZ. So in this route, there is a high chances that if you have an excess of propylene oxide, all the DPZ, not all the DPZ, most of the DPZ that is produced might convert it to the TPZ. Now we have another route, that is synthesis using glycerine, bio-based route. This is maybe the current or the route of the future, because here from biomass we produce triglycerides, and then when the oil splitting or biodiesel, glycerine refining, we will get biodiesel from triglycerides, and then we will get glycerine. From glycerine, after dehydration we get acetol, that is an intermediate, and by doing hydrogenation we got 1,2-propanediol or propylene glycol. So this is a reaction. You can see I have taken this from the Air Liquide company slides, and here the biomass conversion to DPZ to DPZ. Here this is the route that will be the futuristic route, because the future of chemical is moving toward more on the biomass or more on the sustainability side. So this will be the most used route. So till now, what we have discussed the total 6 route to produce DPZ, why different reactions and why the different raw materials. So that now next, so we explore these so that we know what kind of chemistries are available to produce our desired product, and this will help us to segregate or to choose a reaction which will be the best of the current reactions, current routes available, and based on our geography we will choose the reaction, and we will go ahead to produce the flow sheet to produce our desired chemical. So this is very crucial when we are doing our final year project. Like I explored the different route, you should also explore the different routes, collect the different data. Like here in this route you can see we have collected the data of the catalyst performance. So you should also catalyst performance and selectivity, so that when you are choosing the route, you already had the desired data that is required to do the few calculation before we finally converge to the some routes. So you always, when are gonna develop a chemical plant, you should find out the different routes that are possible to produce that chemical. Uh, don't directly jump to the industrial best approach, because sometimes you will find the approach that is used in industry may be outdated, and industries are utilizing that because they already have designed their flow sheets and purchased the equipment according to that. So converting them into some different process will be difficult or will not be feasible until and unless this new process or their old process will become obsolete. So directly taking the data from industry, it is very important to go and explore the chemistry over the research papers, and then find out the different routes that can produce the desired chemical. So this is my advice for you when you are doing your final year projects.